All right. Thank you everyone for tuning in. My name is David Lloyd and I'm a software engineer at Red Hat. Today I'm going to be talking to you about the Qbicc project. To start with, I'll be giving some background on static images in general, how Project Leyden fits in, a bit about the terminology that's being used, what Qbicc is and why we've developed it, what you need in order to run Qbicc, a bit about how it actually works, where we are at in terms of project status, and how to try it out or contribute. So let's get started. So why static images? Static images potentially give us some critical benefits. One key benefit is fast, or in the best case, instant startup. In cloud deployments generally, but particularly in cases such as functions and serverless deployments, instant startup is critical because, in the worst case, the time spent on each request will include the time it takes to start up the program. If the program takes a while to start up or warm up, this can dramatically impact the overall latency and response time of the program, not to mention the incurred CPU costs that may accumulate quickly. Another important benefit is a potentially much smaller footprint. A static image contains only the exact program that is being run and nothing else. This means that unused classes and metadata will not be a part of the final image and thus will consume neither disk space nor memory. This could potentially put Java on a par with statically compiled languages such as C or Go. The end result is higher density per dollar. To talk more about static images in Java, we first need to talk about Project Leyden. Project Leyden was announced in April of 2020 by Mark Reinhold, the JDK project lead of OpenJDK. The stated goal of this project is to improve the Java platform's historically slow startup time, slow warm-up time, and large footprint. Project Leyden proposes to solve these problems by introducing a concept of static images to the Java platform in the JDK, defining the term static image and a few other key related concepts such as closed world and build time. But what is a static image anyway, and what is the difference between a static image and a native image? The term native image in the context of Java is used informally to describe a standalone executable binary file made from a Java program that the target operating system can directly execute. I use the word informally because there's no standard or specification which defines this word in concrete terms. The term is generally accepted to mean that the program is not interpreted, but rather directly executed by the target system's CPU. The GraalVM project prominently features a subprogram intuitively called native image, which produces native images from Java programs and is in fact what the overwhelming majority of users are using to produce native images today. The now defunct GCJ project, which was a part of the GCC project, added the ability to compile Java programs to GCC, including the ability to produce an executable binary, which would almost certainly fit this definition. By contrast, programs made with the JLink and now defunct JAOTC utilities that ship with OpenJDK would probably not fit this definition because they rely on either including or requiring the presence of a standard JDK distribution in order to function. The term static image is defined somewhat more formally by the Project Leyden announcement. There are two parts to this definition. The first is that a static image is derived from one single application and is meant only to run that one application. And the second introduces the concept of a closed world, which in turn essentially means that new classes cannot be loaded or defined at runtime. Project Leyden announcement also talks about formalizing the concept of build time, specifically in the context of class initialization. The primary benefit of these constraints is expected to be that a program can be analyzed thoroughly, allowing the total size of the program to be reduced and allowing initialization of some or all of the program to happen during compilation. Since native images, as we've informally defined them earlier, do fit the definition given for static image, it follows that native images are a kind of static image. However, according to the definition of static image given in the Leyden project announcement, not all static images necessarily must be native images. It would be possible, for example, for a tool along the lines of JLink to produce something that could fit the definition of a static image without being a native image. GraalVM's implementation imposes additional constraints that are not defined in the initial announcement of the Leyden project, for example, additional restrictions on reflection. Mark Reinhold did, however, follow up the original announcement with some clarifications, where he expressed that he expected, for example, that arbitrary uses of the invoked dynamic bytecode under Leyden would likely be restricted similarly to how it is restricted in GraalVM, and that other existing GraalVM limitations might overlap with Leyden as well. So the formal definition of static image seems likely to evolve somewhat. So what is Qbicc? Qbicc is an experimental cross-compiler for compiling Java programs into executable binary static images. Qbicc is written on pure Java and will run on any JDK. What are the requirements for using Qbicc? Qbicc is written in Java, so it requires that a JDK be present on the host system. While Qbicc only requires Java 11 for now, we're expecting to make the move to 17 in the very near future, so users should expect that they will need to be running Java 17 or later in order to use Qbicc. Additionally, Qbicc requires that a C toolchain be installed. A toolchain is a collection of programs used for producing software, which is commonly distributed in conjunction with the operating system. In our case, a C compiler and a linker are required. At present, GCC and Clang, and hence Xcode, are supported, but there is an SPI which allows other C compilers to be supported as well. Finally, Qbicc requires that LLVM be installed in the system, since that is what it uses for its backend, or final stage. The backend is also pluggable by way of an SPI. So why Qbicc? Qbicc is meant to allow rapid prototyping of ideas, so we can, among other things, answer a series of questions about ways that static image production can be improved and eventually standardized in Java. We hope that this research can feed back into OpenJDK and the standardization effort around Leyden, and also to GraalVM's native image implementation. And we want to eventually evolve this project into a complete and compliant implementation in its own right, with some different design trade-offs compared to what GraalVM has made. So what questions are we trying to answer? First, we wanted to determine whether it was possible to create a native image compiler purely in Java. The current popular implementation, GraalVM, presently requires a special JDK to be installed. GCJ was written in C++, being part of the GCC project. So is a pure Java implementation possible? Qbicc is written purely in Java, though the word pure is doing some heavy lifting there. We're actually producing an LLVM intermediate representation, which is compiled on the back end by invoking the LLVM compiler using the Java Process Execution API. Now, an earlier prototype was able to produce ARM 32-bit assembly directly from Java using a custom assembler, but even then, the platform C compiler is used, also via the Java Process Execution API, to gain information about the target platform, which is not something that is really feasible in Java, which is aggressively platform neutral. But in the end, we're able to perform a native image compilation, which works on most systems, which include a C compiler, simply by executing Java artifacts downloaded from Maven. So that really satisfies the definition for any practical purpose, and that's what we're after. So the answer is yes, this is definitely possible. Another important question that we're trying to answer is whether it is possible to further improve startup time, since it's seeming more likely that the cost of startup time is going to be a major factor for many cloud deployments. GraalVM is making a pragmatic move towards runtime initialization of the JDK and libraries by default, in the interest of lowering the bar for compatibility. Project Leyden states that the expectation that compile time analysis would be used to determine what can be initialized at build time versus what must be initialized at runtime. However, not every application needs to be static capable. In fact, I expect that a substantial percentage of existing Java environments would derive no benefit at all from moving to a static environment. So taking great pains to improve compatibility with these existing libraries seems like misplaced effort. We've observed that almost every significant benefit of static images is derived from initializing classes early. Experimentation has shown that even a simple hello world program currently initializes over 100 classes in OpenJDK. Given these observations, I believe it makes far more sense to initialize all classes at build time, with no exceptions, and that any initialization tasks that must be performed at runtime should be accomplished by some alternative mechanism that should be introduced to the language for that purpose. For example, the concept of lazy fields or lazy constants has been discussed by various high-profile OpenJDK members such as John Rose, Remy4X, and Brian Getz. It seems very possible that a concept like this could be a more natural fit for doing or redoing certain one-time initialization tasks at runtime, and might be a more powerful alternative to class initialization for Java in general. It is my belief that compatibility within the JDK and in third-party libraries will come over time after these language mechanisms have been introduced, by way of, for example, the multi-release jar mechanism. In the meantime, continuing with solutions like GraalVM's substitutions, while considered hacky and certainly not standards material, are likely to be able to pragmatically bridge the gap until mainstream adoption of the more static image compatible techniques have been taken hold. So their answer here is maybe. It's really too soon to tell. Hopefully we'll have a clear answer in the months to come. One question that came up earlier in our design process related to how we can take advantage of the static nature of the compiled program to reduce the size of objects. The object header is a part of every object that is allocated by the program. So we've been looking at what we can do to keep the object header as compact as possible. The OpenJDK hotspot implementation uses 128 bits for an object header. That's 16 bytes. That's a lot. Since Qbicc produces static images, we have approached the problem of object headers from that perspective by taking advantage of the closed world as much as possible. First, we're using a numeric type ID rather than a pointer or a reference to a class. Since new classes cannot be defined at runtime, and thus we know exactly how many classes the program will need, by using a numeric type ID, we can use as few as 16 bits for smaller applications like microservices that do not depend on a large number of classes at runtime. We can store all of our reachable class objects in a single flat array, meaning that we can derive a pointer to the class by adding the array base to the type ID with a scale factor, which is something that CPUs are really good at, and thus get a reference to the class object from a type ID without even performing a load from memory. Another benefit of using a numeric type ID is that by topologically sorting the class hierarchy, we can reduce some kinds of check caster instance of operations to 1 or 2 integer comparisons. One fairly well-researched concept we're looking into is using fewer bits for the identity hash code and or computing it on demand. The idea here is that newly allocated objects with a short lifespan might never be queried for their identity hash code, and even if they are, they might not live long enough to change location in memory, so their hash code could conceivably be derived only from the address of the object, possibly in combination with a salt value to avoid repeating hash values across generations. Another memory-reducing measure relates to the observation that in many applications, most object monitors or locks are never actually used. So the idea here would be to only create locks for objects as they are needed rather than having a lock word on every object. This is a relatively old technique that is commonly employed by JVMs today and has been shown to be effective. Qbicc also uses a first fit algorithm for field placement. This algorithm is useful because many CPUs require larger data types like 32 or 64-bit integers and floating point numbers to be aligned on 4 or 8-byte boundaries. This can potentially leave holes when a larger field is placed after a smaller field. So Qbicc tries to fill these holes when a subclass has a field that could fit into space left in a superclass's object layout. Further improvements are possible here as well. For example, we could sort fields by size to ensure that all smaller fields get grouped together, reducing the likelihood of holes, but this has not yet been implemented. The upstream OpenJDK project has a subproject led by my colleague Roman called Project Leyden, whose goal is to effect some changes to a hotspot to explore some of these same ideas and more. So solving this problem looks pretty good so far for both Qbicc and the upstream OpenJDK. Another area of interest relates to how polymorphic method calls are dispatched. vtables and itables are the mechanism by which polymorphic method calls are dispatched on objects. Since the actual runtime type of an object isn't necessarily known at compile time, the type of the object has to be examined to determine which actual method to call. But these tables often take up a significant amount of space. For example, a class can implement just about any combination of interfaces or none at all. So if you keep a table that's keyed by the object's numerical type identifier and a numerical identifier for each method, the table is going to be very large and it's going to be pretty inefficient, containing a lot of gaps. Thus, it is common to trade size for speed by keeping more compact lookup tables using various techniques at the cost of a more expensive lookup. While this is a well-explored problem space in dynamic JVMs, static images give us an opportunity to re-examine this problem from some different initial assumptions. There are some commonly employed mitigation techniques that are employed in dynamic JVMs to avoid the expensive lookup. One of the more effective optimizations is called devirtualization, where the compiler is able to narrow the possible types that are considered for dispatch down to 1 or 2 possibilities. If there's only one possible type, then there's no ambiguity, and the target method can be selected exactly. If there are some small number of possible types, perhaps 2 or 3, then it may be more beneficial to perform a simple comparison to determine which implementation to call, as opposed to a potentially more expensive table lookup. These techniques are also useful in the context of static images, but there are more techniques that the closed world constraint makes available to us. The concept of selector coloring is particularly interesting. With this technique, 2 different method selectors can be assigned to the same slot or color if they're never implemented by the same class. Several algorithms can be derived from this technique that can substantially reduce the size of dispatch tables without necessarily increasing the cost of lookup. These techniques rely on static knowledge of the application, which is generally not available to dynamic JVMs, but becomes possible in the closed world. So in conclusion, yes, it looks like we'll be able to do some interesting things with dispatch, though the implementation isn't quite there just yet. Cloud environments now commonly support multiple CPU architectures, and the IoT space brings in even more possibilities. Additionally, it is often the case that in the Java space that developers are working on a completely different operating system or CPU architecture than the one they intend to deploy to. Consequently, one of our original research questions with regard to static images is whether cross-compilation of a Java static image is in fact feasible. Within Qbicc, we rely on using a C compiler to compile test programs or probes to learn things like the size and layout of important native data types and structures. We're able to dynamically craft C programs which perform tests against these data structures, storing the result in constant global variables, which we would then read out of the resulting object file without having to actually run the C program, which of course would be impossible if the CPU and/or operating system differed between the host and target environments. Thus, we can employ a C cross-compiler for these tests, even if the target is not in any way compatible with the host. Using the cross-linker from the same toolchain allows us to produce the final executable for the target architecture. Since LLVM supports many different CPU targets, and OpenJDK supports many different operating systems, in combination with this technique, we can conclude that yes, it absolutely is possible and even practical to support cross-compilation from a Java static image generator. One common complaint about native image generation today is that it can be very, very slow. We wanted to find out whether it's possible to use different compilation techniques which are faster to execute and still get a pretty good final image. Fast turnaround is something that is particularly important, especially during development. Waiting several minutes to see the results of a small code change is not a good use of developer time and additionally consumes a substantial amount of CPU and energy. This is something that GraalVM is also facing, and it is my understanding they're doing some explorations in this area as well. What we'd like to see is for compilation to be fast enough that it can be used in settings such as Quarkus's dev mode, where the program can be quickly rebuilt and relaunched in real time as changes are made to the codebase. Presently, our Qbicc compilation phases and optimizations are very fast to execute. However, after we hand off the program to LLVM, that stage is much slower and consumes a great deal of CPU. We're still researching this, but it looks like one possible cause is that LLVM may be doing a lot more work than we need it to, perhaps repeating optimizations that we've already performed. So it might be possible to reduce the number and types of optimizations that LLVM is performing and thereby get a much better compile time. Another thing that might be possible would be to support a mode of operation where we can tell LLVM to produce a result as quickly as possible while performing little or no optimization at all, which might allow for this kind of static image dev mode. Additionally, LLVM 13 will be moving to a new pass manager, which initial tests show may be faster by as much as 15% overall, providing another boost towards better compile times. So the answer here is we haven't achieved our goals for compilation times, but we haven't given up yet either, so watch this space. OpenJDK itself is implemented using a hybrid of Java and native code, which it interfaces with using the JNI or Java Native Interface mechanism. One thing we want to explore more thoroughly is implementing the native parts in Java using a foreign function interface or FFI to call the native functions which are specific to the target operating system. One reason this is desirable for static images is that the static image compiler can then include the entire JDK in its reachability assessment. Therefore, only the JDK bits which are actually used at runtime will be included in the final image. No JDK or JDK libraries would need to be present in the target, which is especially interesting in mobile and embedded or IoT situations. And it avoids the overhead of requiring the inclusion of JNI interfaces and the cost of actual JNI dispatch, which can be non-trivial. In particular, JNI libraries, including the JDK, often aggressively look up fields and methods using a reflection-like mechanism, forcing those fields and methods to be available even if the corresponding native code is never actually used. Using FFI instead of JNI was the original approach taken by GraalVM's native image tool, which we liked very much. In fact, I and a few of my Red Hat colleagues contributed a decent amount of implementation code for this, so we understand pretty well what it entails in practice. Unfortunately, they determined that it was too expensive in terms of resources within Oracle to maintain what amounts to a parallel codebase to the JDK. So before they could complete this idea, they switched over to requiring JNI to be present and linking against the native JDK library. GraalVM uses special linker techniques to try and avoid including parts of the JDK that aren't used by the final image as well. But since that decision was taken, Project Panama has been approaching maturity. This is a project that introduces a greatly improved foreign function interface to Java and the JDK using the newer method handle infrastructure. So already a few people have been poking around at the idea of using these no FFI mechanisms to replace some of the native code found in the JDK today. While Panama is not yet merged, it's looking likely that this might happen fairly soon. But even after it is merged, it will take a lot of time to port all the JDK over. There is a large amount of native code in use in JDK today. So within Qbicc, we're trying the original GraalVM approach using Qbicc's FFI mechanism, which is designed specifically for the purpose of making this as easy as possible. Once Panama is merged, we should be able to begin to utilize that mechanism for this purpose as well, which will make it possible to contribute changes to upstream OpenJDK. We could then potentially start to move to using the Panama approach exclusively within Qbicc, depending on how well things shape up in this area upstream. In conclusion, this seems feasible, but time will tell. So how does Qbicc actually work? In its most basic sense, Qbicc simply accepts an application class path or module path in combination with JDK artifacts and the Qbicc class library supplements, and does some hand-wavy magic and produces an executable file at the end that you can then execute in your target environment. This is substantially very similar to GraalVM or to any other static compiler, really. But what's inside the box? The Qbicc project is divided into around 50 or so modules with various responsibilities. These modules can be grouped into several broad categories as seen in this diagram. A core design principle of Qbicc is the encapsulation of independent functionality into isolated modules, which are connected through the use of APIs, which are as simple as we could possibly make them. In this way, most of the functionality of the compiler can be reused, replaced, or generally tinkered with without a lot of far-reaching effects. This allows us to try out different ideas with a minimum of risk in terms of impact on code size or maintainability, and also means that the design itself is fairly simple, at least by compiler standards. Next, I'll go over some of the core pieces of the system. The main entry point is what sets up the compilation system. We have a main class which can be configured using a standard builder pattern. It also contains a main method, which is responsible for reading command line options using the Pico CLI library, which I mentioned because it's a really nice library, and applying them to the builder. Using the builder configuration, it sets up the driver, giving it information such as what's being compiled, how it's being compiled, where to put the result, and what other things need to be done along the way. This includes configurations such as what optimizations to apply, what the target platform should be, and characteristics and defaults to use for the final runtime. Once this is done, the main entry class sets up and runs the driver and gets any errors or warnings from the driver and outputs them for the user. The driver module sets up and controls the entire compilation process. All the plugins which do the work of class initialization, program analysis and transformation, and even debug logging have to be registered with the driver, which processes the program through phases of compilation. There are a variety of hook points that are available to plugins which allow them to interact with all aspects of the compilation process. The driver is in charge of managing the parallel compilation of the program using a work list that is coordinated among compiler threads managed by the driver. It keeps track of compilation errors and warnings and will fail after any phase which reports errors. In order to have something to feed into the compiler, we rely on a class file abstraction which lets us translate what's in the class file into a format that we can understand. In particular, when loading classes, we need to be able to access the fields, method bodies, constant tables, and attributes all found in different parts of the class file. Our class file abstraction understands how to define classes in terms of the compiler's type and member definition APIs. We also use this class file representation to access the bytecodes of the executable members of the class, which include methods, constructors, and the initializer of the class. Since we only compile methods and constructors as they're reached, we don't want to process the entire class at once. So the class file API lets us access information as we need it, including the code attributes where the bytecodes of the executable elements like methods and constructors are found. The method parser iterates the bytecodes of each executable member that is reachable and uses the compiler API to construct the graph format that is used by the rest of the code base for analysis, optimization, and output. The APIs provided by the class file abstraction can be reused by the code base to examine things like annotations or generic type information, which plugins can then use for various purposes. The compiler is the heart of Qbicc. It contains APIs to build, transform, and traverse program graphs. The graphs are represented using SSA, or static single assignment form, which is a graph representation that is commonly used by compilers. This form lends itself well to various typical compiler optimizations. The graph uses an object-oriented node type hierarchy to represent values, operations, control flow, and so on. The graph building API is pluggable so that any plugin has an opportunity to intercept and transform the graph as it is being built. This allows for many simple opportunistic optimizations which can operate on local data, such as removing redundant arithmetic constructs or removing branches with constant conditions. It also makes it easy to perform transformations to canonicalize the program graph, which means to pick one specific representation for certain things, which could otherwise be represented in more than one equivalent way. This is also the mechanism by which many implicit bytecode behaviors are implemented, as I'll describe next. Once the program graph is built, it can then be visited using the Node Visitor API in various ways, which allows for plugins to perform analyses at the subprogram level. These two APIs are combined to allow for interface transformation, where the graph is copied and optimized between each stage of compilation. By using the result of analysis from a previous phase, combined with a Builder API hook, with Builder API hooks on the next phase, A plugin can use this transformation operation to perform optimizations with a wider scope of input without necessarily impacting performance of the compiler to a significant degree. Plugins are what do the actual work of the compiler, and this is where most of the interesting functionality of Qbicc resides. In Qbicc, a plugin is a module which contains classes which implement one or more of the compiler SPIs. We have around 30 plugins right now which perform a variety of tasks. All optimizations, including those which take advantage of closed world analysis, are implemented as plugins. Java language features that are represented by high-level nodes such as try, catch, object monitors, and synchronization, arrays, and so on, are all implemented by plugins. And we also pass classes to the interpreter for initialization from a plugin. Plugins also perform code transformations for correctness by adding in behaviors that are implicit in bytecode but must be made explicit in the final program, including range and null pointer checks, division by zero, cast exceptions, errors that result from missing classes and methods, and so on. Transforming the program graph to a form that the backend can consume is also done by plugins. Since machine code does not have a concept of things like virtual method dispatch, we have to transform these constructs into instruction sequences that correctly implement those behaviors. And right now, this is done in the lowering plugin. The LLVM backend has slightly different rules or restrictions for certain operations compared to what the JVM specification requires, so those differences are accounted for in the LLVM plugin. We also implement our object layout algorithm in a plugin, as well as heap serialization and a few other things as well. The interpreter is what allows us to initialize classes at build time. Using the compiler graph traversal and scheduling APIs, the interpreter works by simply visiting each node and performing the corresponding task, recording the result of executing each node. It's also possible for the interpreter to intercept some method calls and implement their behaviors in Java in the host environment. In this way, it is possible for the interpreter to execute code even before type IDs have been assigned and before the final object layouts are known. The result of initialization by the interpreter is a final build time heap made up of a graph of objects, which can then be further traversed for the purposes of optimization, reachability, and eventually serialization into the resultant image. The interpreter also makes it possible to emulate other core operating systems and CPU types so that a program that is cross-compiled doesn't have to deal with the disparity between the host and target platforms. We use a toolchain API, harness API to make it easier to talk to the C compiler for the target, which is what allows us to dynamically learn information about the target. The API lets us easily compose C programs as strings and pass them to the compiler and get an object file result that we can parse and analyze. It also provides a facility for relaying errors and warnings reported by the compiler or linker to the driver so that all of that information is collected into one place. Finally, it gives us a platform-agnostic API which we can use to look at the contents of object files and read their sections and symbols and get the symbol values. So what's the status of Qbicc? The current status of Qbicc is that we're at a mature state of early development, nearing an alpha release. I would expect this to happen within the next few weeks. What we need for alpha is a little bit more of the base JDK to be supported, so that our Hello World case is a bit more interesting and maybe gives us something to compare with the state of the art and with a normal JVM program. The interpreter still has a couple of issues that should be addressed before we tag, and there are some front-end usability issues that need to be sorted out, specifically that the initial class path to build a functioning image is very, very long. So I'm looking at the possibility of allowing Maven artifacts to be given instead of jar files on disk, which should shorten that dramatically. Everything else could probably wait until after the alpha release. And particularly, we want to keep the door open for experimentation and balance that with our current principles of not breaking things and keeping changes localized. This will let us try out various things and do some A/B comparison and hopefully get some nice data that way. To get Qbicc to play around with or contribute, you can find the project on GitHub at this link. We use GitHub discussions and issues, and in particular, if you're really interested in compiler stuff, then have a look at our GitHub discussions where we have a pinned reading list with lots of cool articles and videos to learn more about compilers in general and about Qbicc in particular. There's a README which shows you how to get started with Qbicc and play around with simple programs. We also have a real-time interactive developer chat using Zulip at the address on the slide. They have SSO, so you don't have to create a new account. Just sign in with your GitHub account or whatever. They're usually fairly active on we're usually fairly active on the Zulip chat and on GitHub. If you don't prefer yet another chat client, feel free to use the Q&A section in GitHub discussions. There's going to be a 5-minute Q&A starting in a moment. Also, feel free to follow up with questions on Huva or the GitHub project or Zulip if you prefer. You can get a copy of the slides from the conference website in order to get those links as well. So thanks for listening. I am going to start going with some questions here. The first question is, do you see a future where all of Java will be natively compiled, or do you think there will be always room for other optimizations, e.g. JIT? Well, as I said, I think it's likely that not every program is really going to benefit because the JIT is still a very powerful tool and in many cases can execute things more quickly, more efficiently than a statically compiled program. And the reason is that a JIT can analyze the program as it runs and learn from it and rewrite the code dynamically at runtime, which obviously static image can't do. That said, I think it's always going to be a scale of trade-offs. So I think in some cases you're going to want the performance benefits for long-term applications that a JIT can give you. And for some cases, you're going to want the fast startup and tiny image size that a static image could get you. So I think the answer is, I think, I don't think all of Java will be natively compiled, but I think that we'll see a balance depending on the application. All right, so I think that's the only question that we've had so far. So I guess that's all I've got. Feel free to join us at the Zulip chat or the GitHub project. I'm going to answer some questions on the Whova Q&A if anyone prefers to use that to follow up. So thank you very much.